What is geothermal heating? Let's talk about how it works, concepts, and ground temperature. At a depth of below 4 feet, the ground temperature stays at a constant 50 to 55 degrees year-round. During the winter, a geothermal system absorbs this extra heat from the earth and transfers it into your home. During the summer, the system takes heat from indoors and moves it back underground. Annual air temperature, moisture content, soil type, and vegetative cover, trees and plants, all have an effect on underground soil temperature. As you might expect, the Earth's temperature changes in response to weather changes, but there is less change at greater depths. In a geothermal heating and cooling system, the heat pump is connected to the building by a distribution system, most commonly air ducts, and the heat pump is connected to the earth through a series of pipes called a loop, which was previously described above. The system exchanges heat with the earth, meaning that no noisy or unsightly outdoor unit is needed. You can see in this photo how the system works during the summer. The house temperature is 68 degrees Fahrenheit, outside air temp is 95 degrees, and the ground temp is only 55 degrees, which is much lower than the air temperature. In the next photo, I will show you how the system operates during the winter. The house temp is 73 degrees Fahrenheit, outside air temp is 20 degrees, and ground temp 55 degrees. Let me explain how the pump transforms this temperature into heat or cold. Vapor compression cycle. All heat pumps use a vapor compression cycle to transport heat from one location to another. In heating mode, the cycle starts as the cold liquid refrigerant within the heat pump passes through a heat exchanger or evaporator and absorbs heat from the low-temperature source, fluid circulated through an earth connection. The refrigerant evaporates into a gas as heat is absorbed. The gaseous refrigerant then passes through a compressor where it is pressurized, raising its temperature to over 180 degrees Fahrenheit. The hot gas then circulates through a refrigerant-to-air heat exchanger, where the heat is removed and sent through the air ducts. When the refrigerant loses the heat, it changes back to a liquid. The liquid refrigerant cools as it passes through an expansion valve, and the process begins again. Although heat pumps are complex internally, they are marvels of compact design for reliability. Some include features such as additional heat exchangers for water heating and microprocessor-based automatic controls and protection devices. Anatomy of a geothermal heat pump. Instead of producing heat like a conventional furnace, a geothermal system moves heat from one place to another. The example below illustrates the summer cooling process. The cool, liquid refrigerant enters the indoor coil during cooling. As it enters the coil, the temperature of the refrigerant is between 40 and 50 degrees. As warm, moist room air passes over the cool coil, the refrigerant inside absorbs the heat. The new, cooler, drier air is circulated back into the room with a blower fan. The refrigerant moves into the compressor, which is a pump that raises the pressure so it will move through the system. The increased pressure from the compressor causes the refrigerant to heat to roughly 120 to 140 degrees. The hot vapor now moves into the condenser, the underground loops, where the refrigerant gives up its heat to the cooler ground and condenses back into a liquid. As the refrigerant leaves the compressor, it's still under high pressure. It reaches the expansion valve, where the pressure is reduced. The cycle is complete as the cool, liquid refrigerant re-enters the evaporator to pick up room heat. During the winter, the reversing valve switches the indoor coil to function as the condenser, and the underground piping to act as the evaporator. In short, the indoor coil and underground piping cause the refrigerant to change state, absorbing and releasing heat through boiling and condensing. The compressor and expansion valve move the refrigerant through the system by changing the pressure. Geothermal advantages. Efficiency. Geothermal heat pumps are much more efficient than air source heat pumps because earth temperatures are much more uniform through the year than air temperatures. Not only are earth temperatures more constant, but also the range of temperatures in groundwater is rather small in the United States, varying from upper 40s to upper 70s nationwide. Geothermal heating and cooling makes sense. Geothermal systems are efficient, environmentally sensitive, comfortable, and economical. Operating savings often provide paybacks of considerably less than 10 years, sometimes less than 5 years if you buy a commercial unit. In addition, electric utilities are so convinced of the value of this technology for their customers that they offer design assistance, referrals, or financial incentives to defray the cost increment of geothermal systems. The key is that geothermal heat pumps use electricity to move heat, not to generate it by burning fuel or using electric resistance elements. Indeed, the U.S. EPA has found that no other technology with more favorable operating efficiencies and economics than emerging geothermal heat and cooling systems. An important renewable energy technology. The U.S. Environmental Protection Agency has concluded that well-designed and properly installed high-efficiency geothermal heat pump systems produce less environmental harm than any other alternative space conditioning technology currently available. On a full fuel cycle basis, emerging geothermal systems are the most efficient technology available, with the lowest CO2 emissions for minimum greenhouse warming impact. Overall, the EPA found emerging geothermal heating and cooling systems to have the lowest environmental cost of all technologies analyzed, including air source heat pumps and natural gas furnaces. Geothermal heat pump systems work. No existing space conditioning technology offers greater comfort, economy, or environmental benefits than the geothermal heat and cooling systems now available for residential and commercial installations. Over 250,000 installations are in place in the United States today, and the number is rapidly increasing. More than 95% of all geothermal heat and cooling customers are completely satisfied with their systems. Let me show you an example of a geothermal system. Closed-loop systems, vertical loops. If the soil conditions are not conducive to trenching, a vertical loop may be the choice. Vertical systems are used where land is too rocky for a horizontal system and for commercial or educational facilities. Spacing vertical boreholes can be in any variety of ways: lines, squares, rectangles, grids, depending on available land area and system borehole requirements. The ground heat exchanger may be either series or parallel piping. Closed and open loops. There are two basic types of loops: closed and open. Open loop systems are the simplest. Used successfully for decades, groundwater is drawn from an aquifer through one well, passes through the heat pump's heat exchanger, and is discharged to the same aquifer through a second well at a distance from the first. Generally, 2 or 3 gallons per minute per ton of capacity are necessary for effective heat exchange. Since the temperature of groundwater is nearly constant throughout the year, open loops are a popular option in areas where they are permitted. Open loop systems do have some associated challenges. Some local groundwater chemical conditions can lead to fouling the heat pump's exchanger. Such situations may require precautions to keep carbon dioxide and other gases in solution in the water. Other options include the use of cupronical heat exchangers and heat exchangers that can be cleaned without introducing chemicals into the groundwater. Increasing environmental concerns mean that local officials must be consulted to assure compliance with regulations concerning water use and acceptable water discharge methods. For example, discharge to a sanitary sewer system is rarely acceptable. A closed-loop system is being used for the Finger Lakes Institute. Closed-loop systems are becoming the most common. When properly installed, they are economical, efficient, and reliable. Water, or a water and antifreeze solution, is circulated through a continuous buried pipe keeping. The closed-loop system is environmentally friendly because water in the loop prevents contamination to the external environment. The length of loop piping varies depending on ground temperature, thermal conductivity of the ground, soil moisture, and system design. Some heat pumps work well with larger inlet temperature variations, which allow marginally smaller loops. Horizontal loops. Horizontal closed-loop installations are generally most cost-effective for small installations, particularly for new construction where sufficient land area is available. These installations involve burying pipe in trenches dug with backhoes or chain trenchers. Up to 6 pipes, usually in parallel connections, are buried with each trench, with minimum separations of a foot between pipes and 10 to 15 feet between trenches. Vertical loops. Vertical closed loops are preferred in many situations. For example, Most large commercial buildings and schools use vertical loops because the land area required for horizontal loops would be prohibitive. Vertical loops are also used where the soil is too shallow for trenching. Vertical loops also minimize the disturbance to existing landscaping. For vertical closed-loop systems, a U-tube, more rarely two U-tubes, is installed in a well drilled 100 to 400 feet deep. Because conditions in the ground may vary greatly, loop lengths can range from 130 to 300 feet per ton of heat exchange. Multiple drill holes are required for most installations, where the pipes are generally joined in parallel or series parallel configurations. A vertical loop well field, being used for the Finger Lakes Institute, consists of 20 wells drilled to a depth of 100 feet. There are 5 clusters of 4 wells spaced approximately 12 feet on center. The depth and number of wells was determined by the estimated heat and cooling load required to maintain a comfortable environment for the occupants. Slinky loops. Increasingly, slinky coils, overlapping coils of polyethylene pipe, are used to increase the heat exchange per foot of trench, but require more pipe per ton of capacity. Two-pipe systems may require 200 to 300 feet of trench per ton of nominal heat exchange capacity. The trench length decreases as the number of pipes in the trench increases, or as slinky coil overlap increases. Illustration below shows a slinky coil in a pond. Pond loops. Pond closed loops are a special kind of closed loop system. Where there is a pond or stream that is deep enough and with enough flow, closed loop coils can be placed on the pond bottom. Fluid is pumped just as for a conventional closed loop ground system where conditions are suitable. The economics are very attractive and no aquatic system impacts have been shown. Conclusion. Geothermal heating and cooling systems can be connected to the earth in a variety of ways, all thoroughly field-proven. The problem is that the cost of commercial units installed run $15,000 to $45,000 and up. The problem is that nobody wants to invest a fortune and get their money back after years. I don't know about you, but I would like to get my investment back in like 2 months. But what if there was a way for you to enjoy all of the benefits of geothermal energy without having to spend thousands of dollars? For that, I've created this do-it-yourself heat pump journal, which will show you how to build your geothermal heat pump step by step for under $1,000, capable of producing 8,000 BTUs of heat. It's a complete do-it-yourself geothermal guide that will save you thousands of dollars. I am sure that your friends and family will be very impressed with your work, and trust me, they'll want to know how the heck you did it. And you won't find this kind of information in any other guide, I guarantee it. Here's some examples of what's inside. Detailed pictures with every step I've made in building the geothermal heat pump. How to build the ground source loop field. How to build the heat pump. How to create your pipe welding equipment from a mini electric sandwich maker and a Teflon skillet. How to weld polyethylene pipe with the do-it-yourself device. How to dig 18-foot holes for your loops with a geared DC motor and some hand-built equipment. How to test the welds of your loop. How to make your trenches. Handy little tips that I have found along the way that will save you a lot of time and money when building your first geothermal device. How everything connects together. Easy step-by-step instructions that will walk you through the entire process. Safety issues that you must be aware of during this project. Big, colorful pictures, diagrams, detailed dimensions, an explanation of every process to make it as easy as possible for you to follow. And other great stuff, which you will find in 176 pages of this journal. This is really easy to do. I'm a regular guy, not a genius, not an electrician, not the kind of guy who created award-winning science projects in school. With this guide, you will save thousands of dollars of the cost of a geothermal heat pump. Heat your entire house with a 350-watt consumption. That's the power an old TV draws from your socket, and you'll be heating the entire home with this amount of power. Go green and help the environment. Now, I'll get to the price in just a moment. Retail geothermal systems are very expensive. To give you some perspective, a geothermal system will cost you upward of $45,000. But you won't pay anywhere near that to learn how to make your own. You can learn to build as many geothermal systems you want for not $297, not $197. Look, I'm not even going to charge you $97. While this presentation is still online, you'll pay the special price of just $49.97. And the best part is, you don't have to wait for it to turn up in the mail. You can download it to your computer right now and get started on building your first geothermal system this weekend. If you order right now through this page, I'm also going to give you a bonus. Besides the complete journal on how to build geothermal systems for under $1,000, a full course on how to design your own geothermal system by geographical location. In this book, you will learn how big the loops need to be for your geothermal system, how they work, and the different types of loops. This is a must-have for your geothermal education. Let's see again what you get in this package. A complete 176 pages guide in a journal type with all the data logged for each step of the process. Detailed pictures with every step I've made in building the geothermal heat pump. How to build the ground source loop field. How to build the heat pump. How to create your pipe welding equipment from a mini electric sandwich maker and a Teflon skillet. How to weld polyethylene pipe with a do-it-yourself device. How to dig 18-foot holes for your loops with a geared DC motor and some hand-built equipment. How to test the welds of your loop. How to make your trenches. Handy little tips that I have found along the way that will save you a lot of time and money. How everything connects together. Easy step-by-step instruction that will walk you through the entire process. Safety issues that you must be aware of during this project. Big, colorful pictures, diagrams, detailed dimensions, and explanation of every process to make it as easy as possible for you to follow. A full course on how to design your own geothermal system by geographical location. There's no easier way to learn how to do something than to watch someone do it first, step by step. To get your hands on a do-it-yourself geothermal heat pump journal on how to build your geothermal system, plus the great bonus on how to design your own system, just click the big orange button below. Click that Add to Cart button and you will be taken to the order form where you can make your payment, and you will get instant access to the training materials right away. So, click the big orange button right now and get started. Hundreds of people from around the world have successfully used the information in this video guide to build their own geothermal systems. Now it's your turn. Now I can't keep this price up for long, so don't miss out. Place your order now before this video comes down. What if I don't like the guide? Now, you should be skeptical. That's perfectly okay. But I want to take all the risk away for you. If you purchase this do-it-yourself geothermal heat pump guide and decide you don't like it, just shoot me an email and I will process a 100% refund right away. No hassles, no problems. You have 60 full days to look through it, and if it's not for you, just shoot me an email and I will refund you instantly. It's that easy. That's how confident I am that this guide will save you thousands. So, just click the big orange button below right now to get started. Click the Add to Cart button and you will be taken to the order form where you can make your payment. As soon as you pay, you will get instant access to the training materials right away. So, just click the big orange button right now to get started. The question is, are you going to consume thousands of watts to heat your home? Or will you build your own geothermal system and borrow the Earth's natural warmth? Don't delay it any longer. The time to take action is now. Stop wasting money and build your own geothermal heat pump right now. Click the orange button right now, and I will see you on the other side.